Hello again. Thanks for joining us. This is a Q&A edition of Space Nuts. This is where the audience asks us questions and we refer to somebody else. And in today's episode, we are going to talk about whether or not we can see our own reflection in space. That's a question from Tony. Are we living in a holographic universe? Charles wants to know. David is asking about black holes versus light. Who wins that war? And Duncan, liquid planets. Are there any out there? We'll find out on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to sort all of that out is Professor Jonti Horner from the University of Southern Queensland. Hi, Jonti.
Good afternoon. How are you doing?
I'm good. It feels like seconds since we last spoke.
Absolutely. Time flies when you're having fun, I think they say.
Let's muck in, as they say in your part of the world. Let's go to our first question. This one comes from Tony. Hi, guys. Given the cosmos has black holes, gravity waves, gravitational lensing, light echoes and dust cloud reflections, any chance we could ever see a reflection of our Milky Way galaxy? Love the show. Tony from Marrickville, which is a suburb of Sydney. Thanks, Tony. What are your thoughts, Jonti?
I think there's a short answer and a long answer to this. I think the short answer is I can think of nowhere that we could get a resolved image. So we're not going to get something like a mirror held up to reality where we get a beautiful picture of the Milky Way galaxy reflected back to us. The different phenomena that can bend light and change its direction are often linked to the amount of mass. So you've got a black hole or a star or something like that. And under Einstein's theory of general relativity, the idea is that mass curves space. So light tries to go in what it thinks is a straight line, but because the space is curved, it gets deflected by following the shortest path through the curved space. So that's how you get gravitational lensing, how you get light being bent. Now, light's traveling really, really quickly, so nearly all the time, that deflection is relatively small. You're not talking about light changing through 90 degrees. You're talking about it changing through a few degrees at most.
Yeah.
And that kind of, you could link to the idea of the escape velocity. In order to get it changing through a really substantial direction, you'd have to be very close into a black hole or something like that. And at that point, you're almost falling into the black hole and everything is doomed. So you need to set up a really unusual set of circumstances for some light from the Milky Way to be bent by, let's say, 3 or 4 degrees by one source, and then go to another source and be bent again and again and again. That chain of events would probably get only a tiny, tiny little bit. So I think you could imagine a scenario where there are packets of light, photons, from the Milky Way that get back to the Milky Way in that mechanism, but there'd be barely any and we wouldn't really be able to detect them, if there were any at all. If there were dust clouds near the Milky Way, some of the light from the Milky Way would reflect off them. And this is like the beautiful reflection nebulae we see all dotted through our galaxy, the things that we get fabulous astrophotos of. Now, I was doing some astrophotography a few months ago, the Large and the Small Magellanic Clouds, and learning a new photograph processing tool that friends of mine who were incredibly gifted astrophotographers taught me how to use. And playing with that and stretching and bending and fiddling, there's a persistent feature around the Magellanic Cloud that looks like dust that appears to be structured that I thought was, I've overdone it on the image. And then I looked at a different image and the same structures were there at the same time. So there's clearly dust and gas that has been stripped off the Large Magellanic Cloud by the Milky Way that is illuminated enough that it is brighter than the background pitch black of the sky for my camera to pick it up. That means that there is light hitting that and bouncing back to us to see it. And some fraction of that light will be light from the Milky Way. Now, I don't know enough about that debris. I've not been able to find much discussion with it online because I was fascinated when I saw it on these photos repeatedly. But I would hazard that some of the light that is illuminating this gas and dust that is around the Large Magellanic Cloud is light from the Milky Way reflected back to us. But that isn't anywhere near enough to get an image. It's a bit like when you're looking on a really foggy day and the sky is really bright. You can't see an image of the sun from that light, you've just got light scattered at you in all directions.
Yeah.
We lost all of the information. So I think we do get reflected light from the Milky Way coming back and things like that. But to actually get an image, a reflected image like you'd see in a mirror, that to me is beyond the bounds of possibility. The nearest we'll get is finding galaxies that look very similar to our own. So they give us a perspective of what we would look like from the outside.
Yeah, this is one of Fred's great wishes. If we were asked a question not so long ago, if you could do anything, if you could just take a spacecraft anywhere in the universe and look at something that you want to see, what would it be? And Fred's wish was to go outside of our galaxy so he could look at it and see exactly what shape it was. We have a pretty good idea, but we've never been able to image it. We don't know for sure if it's got the number of spiral arms that they assume it's got or anything like that. So that was Fred's, if he could do anything, just at the snap of his fingers, looking at our galaxy from outside was one of his wishes. So Tony, unfortunately, no, we cannot see a reflection of our galaxy in any way or form. We probably are seeing light bounce back to us, as Jonti was explaining, from our own galaxy, but it certainly wouldn't give us an image. But thanks for the question. Great to hear from you. Our next question comes from Charles. This is a short, sweet, but rather difficult one to answer. What do you think of the theory that we live in a holographic universe? Now, this is something I've seen popping up time and time again in the popular press. And I suppose we should explain what a holographic universe is before we decide whether or not we live in one.
Yeah, and this is one of the ones that breaks my head. So your answer to this will be neither good or accurate, I suspect, because this is far from my area of expertise, but I'll do my best. The holographic universe stuff is tied to string theory, is my understanding. And to me, is at the point where you're bordering on the boundary between science and philosophy. Because you're starting to ask questions that we have no way of testing yet. And that's really hard. Now, this all ties down to very mathematical and very theoretical studies of the universe, I think dating back to about the 1990s, where people found that in some versions of the maths of string theory, you can get three-dimensional stuff being represented in a two-dimensional way without losing any data. And it's an answer to some of the issues to do with information and black holes. It's one of the things that led people to suggest that you can get information that goes into black holes is not lost, but might be stored in the event horizon and all these kind of things. Now, my understanding of it, as you can tell by that explanation, is kind of limited. It's not my area of expertise. It is called the holographic principle, and that leads to the idea of the holographic universe. So the idea that you can get essentially a two-dimensional representation of all the data you need to have a three-dimensional thing means that you could have in some way a three-dimensional appearing thing actually only be two-dimensional, a holograph, essentially. So that's what the holograph is all about. And I don't fully understand that, you can tell by the explanation. It's interesting because it's become sufficiently rooted in popular consciousness. And this is a total detour here, but one of the kinds of music I really like to listen to is a genre called symphonic metal, which is a bit bizarre. It's kind of operatic rock. If you think about the kind of stuff Queen were doing, I'd go a little bit more rocky, a little bit more metal than that. It's like that. So you typically have an operatically trained soprano singing. The two biggest groups of that I listen to quite a lot are groups called Nightwish and Epica. And Nightwish have done a couple of science-themed albums where they talk about the origin of life and philosophy and origin of species and all sorts of stuff like that. One of their tracks, which I try and get on the radio occasionally when I do a chat about asteroids, is a tribute to the great scientist Eugene Shoemaker, whose ashes were put onto a spacecraft to the moon, who discovered the comet that hit Jupiter back in 1994. So that's Nightwish. But Epica have an album named The Holographic Principle, which they've always done slightly quirky projects as well. The fact that this concept, this thing that is at the very extreme bounds of theoretical physics and theoretical cosmology, has become sufficiently culturally embedded that rock groups are naming albums after it, is kind of quirky for me. I mean, it shows that it's not a totally brand new idea, because if it was totally brand new, it wouldn't be in the popular consciousness yet. It does make my head hurt. I will wholeheartedly and happily admit that this is not something where I'm an expert, in any way, shape, or form. There are very detailed discussions of it online. Even if you pull up the Wikipedia page, the Wikipedia page is pretty lengthy and links to a lot of references, talks about some of the discussions people have had about it, talks about information density, the people who've proposed all these ideas, gives you links to other places. Now, I know, certainly when I'm teaching, I have to tell people that Wikipedia is not the be-all and end-all. It's a fluid resource, it's subject to change, and it's subject to being incorrect. But with a lot of these topics in the more theoretical parts of astrophysics, or even for astronomy as a whole, Wikipedia tends to be really pretty good, because there's enough people out there who are really fascinated by the field that when they see something wrong, they'll fix it. The errors don't tend to hang around that long. So it tends to actually be a good first resource, so long as it's not your only resource. And the article there about the holographic principle also links to these two albums by different groups that have had the same name, but has a fairly lengthy discussion of a lot of the different ideas behind this, a few links to different types of theorems that are tied to this, and also a good list of 28 references and a couple of sources on top of that, including journal papers, where if you really want to dive into this, you can do. Will be very quickly apparent to you that by reading it for 5 minutes, you already know more about it than I do. And then you can listen back to this answer and point out every way in which I was wrong here. But that's my take on it. Now, with all that said, to get back to the question, what do I think about the theory? I don't think about it very much because it makes my head hurt. But as I say, I think it gets to the point of philosophy. It's if there is something where you can make no testable measurement to differentiate between two different ideas, you're more in the bounds of philosophy than you are in the bounds of science. And it's a bit like that old chestnut of how do I know that anybody else actually exists? The only perception, the only existence I'm aware of is my own existence. I'm aware of my inner dialogue and I'm aware of what I see and perceive. And we implicitly assume that everybody we talk to is a being like us. But it could equally just be a convenient fiction. I could be entirely locked in my own head, having all this as a kind of weird dream. I mean, I'd argue that this question is a good example of the fact that I'm not just locked in my own head and having a weird dream, because I would have never thought of this question myself. But you start getting to points where you are having an argument that is more one of philosophy than it is one of science. And for me, the thing that differentiates the two comes down to prediction and testing of theories. If you have a theory that is new, it should make testable predictions. And I'm not really sure, because I'm not a theoretical cosmologist or a theoretical physicist, if this does and if it does, how they would work. So for me, then I come back to kind of the Occam's razor thing with a lack of knowledge, with a lack of expertise. The simplest explanation to me is just that we are in the universe we see. But it's really fascinating to look into this. It's important to do this kind of work. I'm just not qualified to do it. I don't have the expertise.
Yeah, it sort of connects with another theory that we have created this universe in our own minds as a collective. The physical existence of the universe is a manifestation of us.
Yeah,
I've heard that one before, which is
an interesting one tied to it is simulation theory, which I've also seen musical albums named after, which is the idea that what we live in is a simulation, and it's extrapolating off Moore's law and similar laws about computing power increasing into the future, which is that whilst the universe is infinitely complex, the amount of computing power you would need to fully simulate a universe is not as high as you would think, particularly if you set up your code so you only simulate the bits that are being observed at a time. You don't need to, for example, if you were simulating the Earth and everything, you wouldn't need to simulate the surface of these exoplanets we've discovered yet, because we don't have the ability to see them. So you save a huge amount in processing. So that leads to this argument that you could set up a simulation with the quality of fidelity that we couldn't know the difference. Simulation theory then goes to one step further and says, if you can do that once, it's only a small step from being able to do something once to being able to do it many, many times. So therefore, statistically, it becomes more likely that we live in a simulation rather than the real world, because there'll be millions of universes and only one of them will be real. And it's fascinating. It's really good fun. But again, it's philosophy, because how do we test this? Unless we get to take the pill and step out of the matrix and see it for what it is, how you test between these things is really the challenge for me to make them into a really scientific discourse rather than a philosophical one.
Yeah. The Matrix was a good film in a constructed universe, and the reality was much more horrifying. But great question. And I think that's one that'll be debated for years to come. Thanks, Charles. This is Space Nuts. Andrew Dunkley here with Professor Jonti Horner. Let's take a little break from the show to tell you about our sponsor, Incogni. Now, have you heard of Incogni? This is amazing software, and it's available now for Space Nuts listeners at a very exclusive price. And I'll give you those details shortly. They'll also be in the show notes. But I hear you asking, why do I need Incogni? Okay, suppose you want to clean up your online existence, all the stuff that's out there in the ether about you. And some of that may be very private information, and it could be in the hands of people who shouldn't have it or may soon be. Could be getting peddled on the dark web as well. Or maybe you just don't like the idea of your private information floating around online. Now, you could try to remember every website you've ever signed into since the day dot, and in a couple of years you might have made a dent in it, but that's pretty unlikely, let's be real. So why not get someone with the right tool for the job to clean up after you and clear all that data off the web? That's where Incogni comes in. It'll cut down on spam, identity theft. It'll make you much harder to find online, and your risk of cyber attack drops off too, not to mention having your money stolen. That is the worst feeling there is, and I know because it's happened to me. Right now, Incogni is offering 60% off for Space Nuts listeners, and they back their service with a 30-day money-back guarantee. So if you want to check it out, and I think it's a pretty good thing to look at, check it out at incogni.com/spacenuts, and you can get started today at a very low price. In fact, 60% off. That's Incogni, incogni.com/spacenuts. That's incogni.com/spacenuts. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Okay, Jonti, let's do some audio questions. And this one I thought we'd done, but I remember I did send it to you in name, but I sent you the wrong audio, so we did the other one. And so this is the question I meant to send you a couple of weeks ago from David.
This is David from Seguin, Texas. I got another question about black holes, just like all my other questions. I was listening to the latest episode, and you were talking about light spinning around black holes, and us being able to see the effects later than when the event actually happened. But that got me thinking, if the light goes around a black hole and then starts to slowly get sucked in, would the additional gravity of the black hole pulling on the light increase the speed of the light any faster than the speed of light, or even at all? Because I know when a ballet dancer is spinning and she pulls her arms in, she spins faster. So would that effect be the same on light spinning around the black hole and then getting sucked in? I'm not really sure how that works with light, considering it has no mass, but I appreciate if y'all answered my question. Thank you.
Good on you, David. I'm pretty sure ballerinas don't spin at the speed of light, but could be wrong. They do spin rather remarkably. Look, this is an interesting one. Light is the fastest thing in the universe, I venture to say, and I think in conversations Fred and I have had in the past that nothing goes faster than the speed of light in a vacuum. So I would imagine the answer is probably no, that the black hole can't make light go faster than the speed of light.
It doesn't change the speed of the light. It changes its direction. And if you change the energy of light, because you can't change the speed, what you change is the frequency and the wavelength. So if light is trying to escape from a mass, then you see a thing called gravitational redshift. So light coming up from the surface of the sun will be redshifted a tiny little bit because it's escaping from the gravitational well of the sun. Similarly, if it was falling inwards, you'd expect it to be slightly blue shifted, but it's a very, very small imperceptible thing. In terms of the speed of light being the fastest thing there is, that's where all our models of the universe and everything sits. And Terry Pratchett, in one of the many Discworld books that I love very well, made the point that darkness must travel faster than light, because whenever you turn on a light, it was already dark. I think it's quite nice and poetic. Yes. But in reality, it seems that the speed of light in all of the models we have of the universe and cosmology is this kind of inviolable speed limit of the universe. Now, it might be that when we have a chat in 20 years' time, that'll change the tally, because that's how science works. But at the minute, the speed of light is the speed of light. And there is an implicit thing there that we never mentioned that we should do, that what we're actually talking about there is the speed of the light in the vacuum of space.
Yeah.
So as soon as light passes into a medium, it slows down, and that's why you get refraction. If light goes from air into water, the speed of light in water is slower than the speed of light in air. That's why you get the bending, the change of direction there. With black holes, what's actually happening is that the black hole is bending space, and the light is following a straight path on a curved surface, so it appears to bend, which is subtly different, essentially. Light falling into a black hole, if you could imagine being just outside the event horizon so you're not dead, and you're looking outwards, the things you are looking at would look a little bit bluer than they actually are, because light falling in is getting blue shifted as it comes towards you. Similarly, if you shone a yellow light or a green light laser, I've got one of those for when I do outreach sometimes to point the stars out. If I shone a green light laser out from near the event horizon of the black hole, the light would still escape because I'm outside the event horizon, so the escape velocity is lower than the speed of light. There's an acceleration pulling back. The speed of the light cannot change, but the energy would change, so it would become gravitationally redshifted. So that green light laser would look redder to the observer way beyond the black hole than it would as it leaves in my hand where I'm in the shared rest frame for it. But the speed of light itself would not be changing. Caveat, if the black hole's got a disk of material around it, if it's got material around it, then you're not moving through a perfect vacuum. So you would see a little bit of a change in speed there, but that is a different physical process for a different reason. But it's worth being complete, I guess.
Yes, I suppose so. The other interesting thing about light, which we've talked about before, is that, as you said, it slows down in liquid, but light going through a glass slows down. But when it comes out the other side, it speeds up again.
Yes, and that's like bending back in the other direction.
Yeah. So it's a tricky thing, light.
It is.
Because we take it for granted. We need it. It's something we've adapted to on this planet as human beings. If we were to venture to another planet with a different kind of star, it would be alien to us in more ways than we could imagine, because we are used to a medium-sized star with a relatively bright light. But if you went to a planet with a blue star, a bright blue star, the vegetation would be a different color because it would be having to do a different kind of photosynthesis. You'd see things differently. There's all sorts of weird and wonderful things that light could do in other places. Just theory at the moment, but
it also has to do with reaction. I've seen these articles about a small subset of women who have an extra set of cells detecting color in their eye, which gives them an incredibly more granular and fine ability to differentiate colors. So they're the visual equivalent of super tasters. And they can see something that to you or I would just look like it's a certain color. They can see the hues within that. You see these beautiful images of birds that look very dun and boring to us, but then you see a visualization of what they would look like to another bird, and they're incredibly colorful and vibrant because the birds are seeing at frequencies that our eyes are not accustomed to. Similarly with bees and things like that, seeing into the ultraviolet. And that will be accentuated for objects around, planets around other stars. You then get the oddities. I have had the pleasure of seeing a couple of total eclipses of the sun, one of which I didn't actually see because it was cloudy in Cairns in 2012, but we saw the build-up and the aftermath. And the eclipse itself's awesome, but there's this very weird uncanny valley period in the minutes just before and the minutes just after totality where the sun is a tiny little point because most of it's blocked by the moon. So instead of having a disk, the sun gets smaller and smaller until you've essentially got a single point of light shining nearly as bright as the sun. And shadows change and the behavior of shadows look different when you've got a single point source rather than a diffuse source of light. And that gives everything a very uncomfortable, slightly unusual feel. You've got very cool effects like standing under a tree and all the leaves are blowing and all the gaps between the leaves act as pinhole cameras and you get images of the crescent sun on the ground, which is spectacular.
Wow.
Incidentally, on the eclipse trip I went to for the Exmouth eclipse, a lot of people have little pinhole cameras that they made to image the eclipse. And one person had a pack of Jats, which are just an Australian cheese biscuit. Yes, and the holes in the biscuits were perfect pinhole cameras. And they had a snack. So when the eclipse finished, nobody was hungry. It was absolutely brilliant. And I'd never even thought of it. So you get all these weird effects. And we take for granted very, very much that our perception is actually what is out there. Yeah. And this was brought home to me. I went to the driving range with one of my PhD students on Sunday. I don't play golf and I'm particularly bad at it. But there's always this thing about what you perceive and how much of the area of your vision that you're actually actively updating and how much of it is just auto-generated by your brain based on old information. And you forget about that. But we actually are, like our eyes are rastering across and we only see a tiny little bit of our vision. Are we seeing true updates? And I've never really seen that demonstrated until I was at the driving range. Because if I hit a golf ball, and I often hit them very badly, but they go up in the air somewhere. And I can stand there and watch where it goes. And it's easy and you can follow it all the way. The minute you look away and look back, you cannot find the ball.
Exactly.
It's astonishing. And you think, when you're just looking at it, it's really obvious. There's a ball there. It's yellow or white against the blue sky. That can't get more obvious. Look away. Totally lost it, even if you know where it was. And that's all down to how our brain is processing the data we're getting. The ball's still there. The ball hasn't miraculously disappeared. And so all these kind of questions, I find it really fascinating, that boundary between the perception and the reality and how much of what we observe is of our own generation, essentially.
Yeah, it reminds me of that famous gorilla experiment. Are you aware of that one? Yeah, that is a very great, it's a great example of what you think you see and what's really there. And I won't try and spoil it for anybody. You can see it on YouTube.
But yeah, they do that in a lot of training for things like police officers and stuff to talk about the fact that people who think they've witnessed something are inherently unreliable.
Yeah.
And it's also what makes it very feasible for magicians and consters and tricksters to trick you by taking your brain off somewhere else. You know, the whole sleight of hand thing is all born of this same thing.
Yeah. Yeah, it is. It's really remarkable. I could talk about this stuff forever. I really find it fascinating. But yeah, lovely question, David. And I hope that it covered you adequately as we strive to do here on Space Nuts. But no, a black hole can't make light travel faster than light.
Roger, you're allowed to clear here also.
Space Nuts.
Our final question comes from a regular sender-innerer from the United Kingdom.
Hello, this is Duncan from Weymouth in the UK here again. Just wondering, is it possible to have an exoplanet that is entirely liquid? So it could just be like a global ocean, but with no solid core, just liquid all the way through. If it's not possible and it has to have a solid core, why is that? And also, how small could that solid core be? Could it be something the size of, say, Everest, or could it be even smaller, or does it have to be something bigger? Maybe the size of the moon? I don't know. What are your thoughts on that and opinions? Do you have any actual answers? Does anyone know? Just wondering, perhaps you could give us some answers with regards to that. Okay, thank you very much. Keep up the good work. Well, until next time.
Thank you, Duncan. I love this question because these are the sorts of things I wonder. Yeah. And look, we've got examples of ice worlds in our solar system. They are ice moons. They have a solid surface and it's thought that they probably have a solid core, but in between, oceans. Yeah. But he's talking about an exoplanet that is pure liquid, just a big blob of water.
Yes. It's a fabulous question. And again, this can have a short answer and a long answer. The short answer is essentially no, but it's not for the reason you're thinking of. It's not to do with the core. It's the fact that nothing can be a liquid that I'm aware of in the vacuum of space. So on the surface of the liquid, you will get evaporation and you would end up with an atmosphere. So you'd end up with a gaseous shroud around it. It doesn't need to be much atmosphere. So technically, it couldn't be entirely liquid because there would need to be gas around it for there to be sufficient pressure that the material on the surface can remain liquid. You could create something, of course, but you'd need it like a bubble around it, a glass shell or whatever.
Yep.
The other reason that in a physical sense it would be very unlikely to have this is that the things that you form are made of everything that's around. Rocky planets don't capture the hydrogen and helium because their escape velocity is too high, so the gravity is too weak. But when you're forming something, you're building a planet, you're building it of everything that is around. So that will include a lot of water if you're somewhere where the temperature's low enough for water to become an ice and to be a solid. But it'll also include iron and nickel and dust and all the other stuff. And you're not going to have a situation where everything you form a planet from would all be liquid at the same conditions. So you'd always end up with some stuff sinking to the middle as solids. What you could imagine, though, is you could have a idealized situation. Let's say you could quarantine an area of space off and you could form something planet mass out of absolutely perfectly pure water ice, so nothing else but hydrogen and oxygen bound together. In that scenario, I could imagine you having a planet that is almost entirely liquid, except for the atmosphere, which would be water vapor, and would probably then quickly become an oxygen-rich atmosphere because once you've got water vapor exposed to UV, it gets dissociated into hydrogen and oxygen, blah, blah, blah. All sorts of stuff happens there. You would then have a situation where, depending on the mass of the object, you could have an object liquid all the way through. If the object is too low a mass, you'd gradually lose it, because if it's of a low enough mass and it's going around a star, the stuff that's boiling off to form a gas will then be moving fast enough to escape. So the atmosphere will be stripped and the thing will essentially boil away like if you leave a pan on the hob. I would imagine that there is also a range of sizes and masses where the pressure in the center gets so high that the water becomes ice again, even at high temperature. And we see this with Uranus and Neptune. There is certainly water ice in the interior of those, but it's a different phase of water ice to that we're used to. I never really understood this, but there is an incredibly gifted Australian researcher called Helen Maynard Casely, who last time I've not seen her for a few years, but she used to work down at Anstow in northern Sydney using devices like Wombat, doing X-ray diffraction and stuff like this. And she discovered several new types of water ice because she was looking at what happens to water at temperatures and pressures very different to room temperature. And that can be really cold conditions like on the icy moons of Jupiter, or it can be really high pressures, or both. And so it's fairly well established that if you increase the pressure, water ice will remain solid at higher temperatures. That this boiling at 100 and freezing at 0 is a function of the current atmosphere pressure we have on Earth, and you change that and it changes.
Yeah.
Incidentally, that's why if you're a bit of a tea aficionado, you cannot get a good cup of tea at high altitude, because water boils at a low enough temperature that it makes a bad cup of tea. You know, but people who went into the Himalayas grumbling about how terrible the tea was, and you're at high enough altitude that the boiling point of water is reduced enough that, and for people listening in America who aren't familiar with this, people, particularly from the UK, are very obsessive about their tea, but to make tea, you need the water to be on a rolling boil at 100 degrees C for many kinds of black teas, green tea and white tea, it's a colder temperature. But when you make tea with lukewarm water, that is wrong. That just doesn't work, and you get a very different behavior, and it's to do with the chemistry of what goes on. So,
yeah, that's fascinating. Yeah.
What else comes into this? Which would lead to, if we ever found a planet that was pure water and was liquid all the way through, that to me would be evidence of the builders of Magrathea from Douglas Adams. You know, it would be evidence that this was a constructed entity rather than something that formed naturally. Because the contamination is the simplest way of saying you wouldn't get a purely liquid planet. You can get a planet that is more liquid than anything else, and we have suspicions that there are these Hycean worlds, these ocean planets. And the reasoning there is that water is actually one of the most common things in the universe. You've got the most common atom with hydrogen. You've got the third most common atom with oxygen. You put them together, you get water ice, or liquid water, or water vapor. So you can imagine planets that have more water than anything else, that are huge oceans with a core underneath them, that are ice and then liquid, then ice again, like we see with the outer moons. But getting something that is liquid from the surface to the core has those problems, one of contamination, and one of you would need an atmosphere to have the pressure to remain liquid.
Fascinating. Yeah, love that question, Duncan. So the answer is probably no, but not far off in some respects. But it might take a megastructure of some kind to create a water world. Although Kevin Costner did find one. Yeah, apparently.
Apparently the costs of going there to film the film were outrageous. So
yes. They're trying to get it all back with a theme park, I think. But yes. Thank you, Duncan. Always good to hear from you. You've always got some great ideas. And if you would like to send us some questions, please do via our website, spacenutspodcast.com, spacenuts.io, and have a look around while you're there. Check out the shop, check out our all the other things. And don't forget to click the AMA thing at the top, which is where you send your questions, text or audio versions. Thank you, Jonti. That was great fun.
it's a pleasure. It's always good to chat. Thank you for having me.
Oh, no, my pleasure. We'll catch up with you next time. Professor Jonti Horner from the University of Southern Queensland. Hugh couldn't be with us today. I don't know what he's been up to, but I do know about today. Apparently he was using a telescope to try and see his own reflection. He's still going. He's been doing it for days, apparently. And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.